Now, chapter 7 is very different from what we saw in chapter 6. Chapter 6 was all about numbers and energy and quantification of things. Chapter 7, we're going back to basics in some kind of way. When we last spoke about atoms in chapter 2, we kind of left off with a cliffhanger of sorts. We understood that there were protons and neutrons and electrons. And we knew that the protons and the neutrons existed in the nucleus, and the electrons existed outside of the nucleus. But aside from that, we didn't really have a whole lot to say. And so to that end, we run into some problems of, when it comes to electrons, we've left it kind of open-ended. And so what we're going to do in this chapter is we're going to talk a lot more about electrons themselves. And what that's going to set up for us is at the end of chapter 7 here, we're going to have a pretty good foothold to begin talking about bonding in chapter 8. Now, your lab this week is all about bonding. We're actually a little bit behind the lab now because of some of the things that we've been doing and just virtualizing things that has really slowed us down in some places. So we're a little bit behind in that regard. I think what we're going to do is we'll see next week. We'll catch up a little bit to what you're doing in lab, and some of the things that you're being asked to do in that lab will make a little bit more sense in the context of chapter 8 next week. But if we look at this from a structural standpoint, first of all, chapter 7, we are not going to cover every single topic in it. Of these topics, these 5 sections that we are covering, we're not going to be going through all of them in the full depth that the book does. We are going to start with the Bohr model, though. The Bohr model of the atom is important to us because it gives for us a picture that we can at least gravitate toward and latch onto as far as what does an atom look like in terms of where those electrons are. Now, of the models of the atom, this is one of the ones that you've probably seen before, the planetary model of the atom. You've got the nucleus in the middle. You've got these electrons circling the nucleus in these planetary rings, kind of like the rings of Saturn, or what you think about our solar system looking like with that sun in the middle and those 8 planets circling it in those orbits. The Bohr model is similar in that kind of way. Electrons are capable of sitting in these orbits around that nucleus. And these orbits represent what we call energy levels around the nucleus. So every single orbit has its own energy, and if an electron wants to go from one orbit to another, it's got to add an appropriate amount of energy to do so. As we add energy to those electrons, they get further away from the nucleus. So each succeeding energy level increases the distance between the nucleus and that electron involved. So from the energy level standpoint, the closest energy level is the first energy level. Each energy level gets ringed out from there. So the second energy level, the third, the fourth, the fifth, the sixth. And even there's another one out here that we can talk about that we know does exist and does have electrons in it, depending upon how big the atom is. So that's Bohr's model. Problem with the Bohr model is that it was largely insufficient to describe the electronic character of pretty much anything other than hydrogen. The Bohr model did a great job at explaining hydrogen and why hydrogen's electrons behave the way that they do. But beyond hydrogen, it had some real deficiencies. It had some real problems. And so a more complex model was necessary to help describe those atoms overall. That more complex model is something called the quantum mechanical model. Now, the quantum mechanical model has a lot of intricate features to it. We're only going to focus on a couple of them. One of the things that we can gravitate toward, however, is the idea that electrons don't exist in orbits, rings around the nucleus, but rather they exist in orbitals, three-dimensional shapes that surround the nucleus. And no, they are not nearly as precise as an orbit is, but they give a much clearer picture about what the electron is doing. So what these orbitals do is they give us an area and says the electron that we are looking for in this energy level exists in this space. And that space we call an orbital. Now, orbitals can exist in energy levels. In a given energy level, you will find different types of orbitals that have roughly the same size. And the size, again, is dependent upon the energy level that they are in. If they're in the first energy level, they tend to be small. If they're in the second energy level, they tend to be a little bit larger. If they're in the sixth energy level, they're going to be larger than any of the other ones before them. One other interesting feature that we can draw is that our orbitals do not all have the same characteristic shape. In fact, there are 4 different types of orbitals that exist. Those 4 different types take on 4 different shapes. And among those shapes, what we have are different sublevels. A sublevel is a group of orbitals that have the same shape in a given energy level. Now, in the S sublevel, there's only 1 orbital. In the P sublevel, there happen to be 3 orbitals. That dumbbell-shaped orbital actually exists in the 3 primary directions. So there's one on the y-axis, there's one on the x-axis, and there's one on the z-axis coming out of the board. The D sublevel actually has 5 different orbitals, 5 different orientations for that clover leaf. The F sublevel actually has 7 different orientations for that dragonfly shape. So with those orientations, if I start to put them together, what I will find is that those combinations together in a given energy level end up producing a general sphere that represents that total energy level where those electrons can exist. And with that in mind, we need to understand a couple of things. As the energy level increases, first of all, we are going to see larger orbitals overall. We're also going to see more possible sublevels and orbitals available as well. So in the first energy level, the only sublevel that is possible is the S. The S has a capacity of 2 electrons. In the second energy level, S is possible, but now we also introduce the P sublevel. The P sublevel has 3 orbitals in total, which means that the second energy level can hold 8 electrons in total. The third energy level is capable of holding S, P, and D sublevels. That makes the capacity of the third energy level 18 electrons. The fourth energy level can hold all 4 sublevels, and as a result, it has a capacity of 32 electrons. So as we go down in energy level, as those electrons get further away from the nucleus, we're going to see that they get larger overall. We're also going to see that there's more room for more orbitals, which means that there's more room for more electrons. The importance of that is going to become apparent on Friday when we start talking about how electrons arrange themselves inside of an atom to maximize that space and minimize their interactions with each other. Because you have to think, all those electrons are negatively charged. Negative charges repel each other. So there's going to be a natural tendency that those electrons are going to want to push away from each other. The way that they arrange themselves inside of the atom actually has a really significant role in their not doing that overall. And so that's what we're going to talk about on Friday. Friday, we are going to talk about that. We're going to talk about electron configurations. And that'll put us about 2/3 of the way through Chapter 7. Chapter 7 is a real short one as well. Any questions?